Medieval carpenters built timber frames that survived 700 winters, and they did it without a single engineering textbook. A medieval timber frame looks, at first glance, like something out of a storybook. Heavy posts, angled braces, dark beams crisscrossing white plaster. It feels romantic, almost accidental, as if people simply stacked big pieces of wood until a house appeared. But that picture is wrong. Behind every medieval frame that is still standing is a set of decisions that quietly obey the same physics and engineering principles used in modern structural software. The difference is that medieval carpenters computed with their eyes, ears, and hands instead of calculators and code. For most of history, if your building collapsed, you did not file an insurance claim. You were crushed, or you froze, or you lost your grain and your animals. That brutal feedback loop turned carpentry into applied science long before anyone wrote a formula for bending moment or shear. The untold science behind medieval timber framing is not that they had secret equations. It is that they turned observation into rules, which shapes survived storms, which joints stayed tight, which beams sagged, and which frames rode out earthquakes while others cracked. Over generations, those rules became a language of posts, beams, and braces that modern engineers now recognize as efficient structures. The first piece of that language is simple. Always fight bending with triangles. A single beam spanning between two supports is a bending machine. Load it from above, and the top fibers compress while the bottom fibers stretch. The longer and thinner the beam, the worse the bending. Medieval carpenters watched beams sag over time in lofts and barns. They did not know the word moment, but they knew the feeling of a floor that bounced, a tie beam that slowly crept downward, a roof that began to sway. Their answer was not to keep making beams thicker. It was to change the shape of the structure itself. Look at a traditional timber frame from the side and you will see it. Triangles everywhere. A pair of rafters meeting at a ridge, tied together by a horizontal tie beam. Diagonal braces running between posts and beams. Cruck frames, those huge curved timbers shaped like an A, creating arch-like forms. All of these are ways of turning a floppy rectangle into a locked triangle. In engineering terms, they move the primary forces from bending to compression and tension along members. A truss carries loads by pushing and pulling in line with the grain instead of asking a beam to resist sideways bending alone. Medieval carpenters did not draw internal force diagrams, but they saw that when rafters were tied and braced, they stopped spreading walls. The mystery science is simply this: triangulation. That triangulation is clearest in roofs. A simple pair of rafters leaning against each other like an inverted V will push outwards at their feet as they carry the roof's weight and any snow on top. Left alone, they slowly shove the walls apart. Medieval builders learned to tie the feet together with a horizontal member, the tie beam. Now, instead of pushing the walls away, the rafters pull on the tie beam, which resists in tension. The load flows down the rafters in compression, across the tie in tension, and into the posts. Add a king post or queen posts between the tie and ridge, and you get more support in the middle, shortening the effective span and reducing bending even further. Modern texts call these king post and queen post trusses. Medieval carpenters just called them good practice. In wide-span barns and halls, they extended this logic. Cruck frames, the huge curved blades hewn from naturally bent trees, were not rustic ornament. Their curved shape placed more wood where bending stress would be highest and allowed the roof load to pass down in a smooth compression curve toward the ground. The outer fibers of the curve go into tension. the inner fibers into compression, a pattern that suits the anisotropic nature of wood, better in compression along the grain than across it, and drastically weaker in tension perpendicular to the fibers. By exploiting natural tree curves, carpenters essentially pre-bent their beams into the shape loads wanted them to take, reducing dangerous stress concentrations. Next comes the part that most people notice without understanding: the joints. Medieval timber framing is famous for mortise-and-tenon joints secured with wooden pegs instead of metal nails. That choice was not just about tradition or the cost of iron. It is deeply tied to the way wood moves and how loads travel through the frame. A tenon is a projection at the end of one timber that fits into a matching slot, the mortise, in another timber. When a peg is driven through both, the joint works in bearing along the grain and in shear across the peg. That means the heavy beam can transfer load directly into the post, with large bearing surfaces and gradual stress transitions, instead of concentrating everything at a couple of metal fasteners. Master carpenters took this further with drawbored joints. In a drawbored mortise and tenon, the hole in the tenon is intentionally offset slightly from the hole in the mortise cheeks. When the peg is hammered through, it pulls the tenon deeper into the mortise with constant tension. The result is a self-locking joint that stays tight even as the wood shrinks and swells with changing humidity. Structurally, this pre-stressing reduces slip and racking under lateral loads. The joint behaves more like a monolithic connection, improving the frame's ability to act as a single, stiff box. The science hiding here is pre-tension, the same principle behind modern post-tensioned concrete, applied with a mallet and a hardwood peg. Look carefully at where carpenters chose to put those joints, and you find even more physics. They avoided chopping big mortises into the middle of highly stressed spans. Instead, they placed major joints close to supports, where bending moments are lower and longitudinal compression and shear dominate. In tie beams spanning between walls, joints to support posts and braces often occur near the ends, not at mid-span where bending is highest. They thickened sections near joints, giving more cross-sectional area for load transfer and reducing stress per unit area. They oriented grain so that tension and compression occurred along, not across, fibers whenever possible. Without ever saying the words stress concentration, they behaved as if they understood it. The layout of an entire timber frame is another kind of silent equation. Viewed from above, many medieval houses and barns use a regular grid of posts and beams, bays, that repeat. This modularity had practical benefits for cutting and assembly, but it also spreads loads more evenly. Every frame, each pair of posts with connecting tie beam and braces, acts as a portal frame that can handle vertical loads and horizontal forces from wind. Connect a series of these frames with longitudinal rails and braces, and the building becomes a three-dimensional box, sharing forces between frames. This box frame behavior is now recognized in structural engineering as a very efficient way to resist lateral loads, including earthquakes. After the 1755 Lisbon earthquake, similar ideas were codified in the famous Pombaline-Gaiola timber infill system. Medieval carpenters had already been hinting at the same logic centuries earlier. Bracing is where their intuition about dynamics really shows. A simple rectangle of posts and beams racks easily under sideways loads. It deforms into a parallelogram. A diagonal brace turns that rectangle into two triangles. Medieval builders placed braces strategically between posts and beams in wall bays, often near corners, to stiffen the frame. But they did more than just throw braces anywhere. Studies of historical frames show consistent patterns: braces that are long enough to be effective, but short enough not to interfere with openings; braces arranged in mirrored pairs to avoid twisting the building, braces placed higher where bending and racking effects are more severe. They understood in their own language that lateral stiffness depends on both brace angle and length. One of the least romantic but most powerful pieces of science behind medieval timber framing is simply knowledge of material properties. Carpenters knew their wood, not as numbers on a chart, but as weight, grain, sound, smell. They knew that slow-grown oak with tight rings and straight grain made better posts and tie beams than fast-grown, knotty material. They knew that sapwood rotted faster than heartwood and kept it out of critical sections. They knew that wood is anisotropic, stronger along the grain than across it, and aligned members so that major forces stayed as parallel to the grain as possible. When they squared logs by hewing, they oriented the heart in ways that optimized strength and minimized checking. Modern conservation work on historic frames has confirmed that many critical members are, by today's standards, conservatively sized and made from higher quality material than most off-the-shelf lumber. Even the way they cut beams speaks to structural thinking. In many medieval buildings, important timbers are not sawn from anywhere in the log but riven, split along the grain. Riving follows natural fiber lines, producing pieces with fibers running straight end to end, free of cross-grain tears and micro-cracks. That makes the member significantly stronger in tension and bending along its length than an equivalent section with grain runout caused by sawing. For braces and curved members, carpenters often sought naturally curved trees, so the fibers followed the curve. This allowed the member to work in pure fiber tension and compression along the curve instead of having to resist tension across grain, exactly the sort of failure mode that leads to sudden brittle breaks. As frames grew more ambitious, large barns, multi-story houses, big civic halls, carpenters moved from purely empirical rules into what we would now call typologies, standardized structural solutions for common problems. Cruck frames provided wide, open interiors with minimal internal posts. Aisled barns used inner rows of posts and arcade plates to reduce span and distribute loads. Long tie beams held walls together, while queen post trusses above allowed open central spaces without huge, sagging members. In some regions, specific patterns like close studding and jettying, upper floors projecting beyond lower ones, developed, each with its own load path logic. Jettying, for example, shifts upper floor loads back toward the interior, reducing cantilever effects and allowing posts to carry combined loads more directly into foundations. These were not random stylistic flourishes. They were iterative solutions to structural and spatial constraints. Connection details reveal another level of quiet sophistication. How to let a building move without breaking. Wood swells and shrinks as humidity changes. Long members creep under load. If you rigidly lock every joint, you store stress until something snaps. Medieval joints, especially in roof structures, often allow controlled rotation. A classic king post truss, for example, may rely on bearing surfaces and pegs that transfer load but still permit slight hinge-like motion at certain points. This turns the truss into a statically determinate system that can tolerate settlement and small shifts without developing large internal stresses. The science word is ductility, but to a carpenter it was simply building forgive into the frame. At the same time, certain joints were deliberately overbuilt to behave more like fixed connections. Halved and housed joints, where one beam sits partly cut into another, create broad bearing surfaces that share load in compression. Splayed and tabled scarf joints, used to join two shorter timbers into a longer span, interlock in 3 dimensions, sometimes with keys, pegs, and wedges that resist both tension and bending. modern analysis has shown that some of these scarfs distribute stress remarkably well along the joint length, reducing peak stress and fatigue. They are physical manifestations of what an engineer would call load distribution and redundancy. The science behind medieval timber framing is not just in the wood and the joints, it is also in how frames were put together. Marriage marks, numerical or symbolic markings on timbers, tell us that frames were often pre-assembled on the ground. Carpenters laid out full-sized frames, flat, assembled joints, checked fits, and then raised the entire bent as one unit. Structurally, this allowed them to verify that all joints pulled tight and that the frame behaved as expected before committing it to height. In large barns, a series of bents could be raised sequentially and tied together with longitudinal members and braces, creating an immediate three-dimensional structure that gained stiffness rapidly as the build progressed. This method reduced the risk of partial, unstable assemblies that might rack or collapse during construction. It is tempting to imagine medieval timber framing as frozen in time, but it evolved in response to new pressures, literally. As buildings grew and cities became denser, fire, wind, and even seismic events challenged old patterns. In some regions, builders experimented with box frames and infill that provided better resistance to lateral loads, especially in earthquake-prone areas. After major disasters such as earthquakes and urban fires, treatises and local regulations sometimes codified timber frame patterns that had proven safer. Later historical analysis of those systems shows many of the same strategies modern seismic design uses. Regular grids, continuous load paths from roof to foundation, and diagonals that help dissipate energy. Yet for all the complexity hiding in the timber, the guiding logic remained surprisingly consistent. Work with the material, not against it. Turn bending into axial forces wherever possible. Lock planes with triangles. Keep joints in low-stress zones. Allow some movement where necessary, and oversize critical members when uncertainty is high. If you step back from a great medieval barn or hall and look at it through a purely analytical lens, you see a set of solutions any structural engineer would respect. Heavy posts carry axial loads into robust foundations. Tie beams prevent walls from spreading. Braces triangulate panels and resist racking. Roof trusses convert wide spans into shorter effective members. Connections are detailed to handle load transfer without crude stress spikes. The building is redundant enough that if one brace weakens, others still share the work. For a curious, practical, nostalgic viewer, the real payoff of this untold science is not just admiring old buildings. It is recognizing that you can borrow the same principles today, even on a small scale. If you're designing a shed, tiny house, or cabin, thinking like a medieval carpenter might mean choosing fewer, heavier, well-placed members instead of many flimsy ones. Using real triangulation, proper braces, rather than relying on thin sheathing alone. Placing major joints near supports and thickening wood where load flows change direction. Letting certain joints act like hinges while making others solid and well-housed. Respecting grain direction, using riven or straight-grained pieces for highly stressed members. You don't need to reject modern tools or codes, but understanding why that old barn down the road is still standing can make your work sharper. It can also answer a quiet question many people have when they stand under centuries-old beams. Did they just get lucky? The answer, almost always, is no. Medieval timber framing works because people paid attention, obsessively, to what gravity, wind, and time were telling them. They watched where frames cracked, where joints opened, where roofs sagged. They changed patterns, refined joints, standardized best practices long before anyone had a name for best practice. When modern engineers model those structures, they often discover that the primitive designs show remarkably good stress distributions, comfortable safety margins, and graceful failure modes. That is the untold science, a world where structural engineering existed, but its formulas were stored in calloused hands, in guild rules, in the angle of a brace, and the slight offset of a peg hole. A world where every timber frame was a solved equation you could walk inside without ever seeing the math.